Sure.
So I was looking at when you number the different chiral, the pieces that come off of the chiral center,
Yeah.
and I just wanted to confirm that we're only comparing like one atom to one atom, not the total sum of the
Right.
molecular.
You start with the first atom, and then if the first atom doesn't distinguish between two groups, then you look at the things that those two particular atoms are bonded to.
Okay, cool. Thanks.
Yeah. Okay, so we'll start, and that'll probably kind of address your question here as well. So we'll go ahead and get started. So all of the examples we looked at yesterday were, oh, well, first, before we get started, does anybody have any questions about the exam? So the exam ended up being curved by 6 points, and that's then changed in Canvas. So your Canvas scores are your graded curved exams. The average was high 60s, which isn't too bad, and so the curve brought the average for our class right around 74. So that's pretty good. Okay. All right. So back to this. So all the examples we looked at yesterday, the molecules only had one chiral center, but that doesn't necessarily have to be the case. In this example, there are two chiral carbons. One is the carbon with this hydroxide, and the second is this one right down here. So when you have multiple chiral centers, each needs its own R or S. Okay, so the drawings get sort of messy because you're going to have to deal with one chiral center and drawing the arrow for the steering wheel separately than this one. Okay, so it doesn't matter which carbon you start with. So I'm going to do this one here in green. The hydrogen is the lowest atomic number, so it gets the number 4 priority. Oxygen has a higher atomic number than the carbon here and the carbon here. So this is 1. And then when you come down to compare these, the first atom you're comparing here is a carbon, but so is this. So it's carbon to carbon. Since these two atoms are the same, you look at the things that are bonded to the carbons that you're in question of. So this carbon is bonded to 3 hydrogens. This carbon is bonded to a carbon in this methyl group, this carbon up here, and then the hydrogen on the dash. So this carbon beats this hydrogen. So this becomes group 2, and this is group 3. So to do your drawing of your arrow, since 4 is already at the back, you just come down 1 to 2, 2 to 3. So at the hydroxide carbon, we're R. Then we have to go do the same thing, but look at the carbon with the methyl group. Okay. So again, here we would have priority 4. And now this carbon is bonded to 1, 2, 3 carbons. So we have to figure out which of the carbon sets is going to be higher priority. So now for this side in the blue, this carbon will play or has hydrogen, hydrogen, hydrogen. This carbon has hydrogen, hydrogen, and this carbon down here. this carbon has oxygen, hydrogen, carbon. So oxygen, hydrogen, carbon. Oxygen beats carbon. So this becomes 1. Carbon here beats hydrogen. This is 2, 3. So now we're going 1 up to 2, 2 down to 3. So the carbon with the CH3 on the dash is also R. Okay. So now I'm going to redraw it so it's a little bit cleaner so we can work on the name. Okay, so we would number in both directions. Now this numbering is for the naming purposes. 1, 2, 3, 4, 5, or you would have to come back. 1, 2, 3, 4, 5. The green numbers are 2 and 3. The blue numbers 3 and 4. Okay, so the green numbers give you the lowest locants for the substituents off the chain. Okay. In parentheses, you would write that carbon 2 is R. Carbon 3 is also R. So you list the stereochemistry here. Then you name it like you always would. This is a methyl substituent. This again is hydroxy. So H comes before M. 2-hydroxy, 3-methyl. There should be a dash there. I forgot. 3-methyl pentane. Are there questions about this example with 2 chiral carbons? If you had 3 chiral carbons, you'd do the same thing.
I have a quick question.
Sure.
I'm a little bit confused. Where did you find when you found the CCH, like when you're comparing the first chiral carbon?
Yeah.
Where did you get those from?
Let me see.
The CCH on the bottom.
Here. So I was comparing this carbon to this carbon. Yes? Can you see my mouse?
No.
Oh. Okay, I'll point. This carbon is being compared to this carbon. So this carbon has a hydrogen, and a hydrogen. This carbon on the dot, this dot here, is bonded to this carbon, this hydrogen, and this carbon. That's why there's 2.
Oh, okay. Yeah, I see it now.
Okay, any other questions?
Yeah, I have one more.
Sure.
So in that first diagram, the numbering, like the direction of the arrows, when you're picking which one's 2 and 3, is that based on like the weight?
No. Don't ever do weight.
Okay.
Because let's say, let me make some room on here. It's a huge long chain over there. Fluorine here. Right? Wait a minute. I want this to be a file. not an SH, not an OH, make it an SH. Okay. So hydrogen would be 4. The sulfur has a higher atomic number than fluorine, so that's 1. Okay, so now you come down here, carbon to carbon. This carbon is bonded to hydrogen, hydrogen, fluorine. This carbon is bonded to hydrogen, hydrogen, carbon. Since fluorine is higher atomic number than carbon, this is 2, and this big long group is 3. So even though, I mean, fluorine's not a heavy atom, it only weighs about 19, but you have all these carbons over here. So this side would weigh more than this side, but you don't use weight, you use atomic number.
Okay, gotcha.
Okay. Any other questions? Okay, so we're going to move on to section 5.4, which is called optical activity. And the important part about optical activity is if you have a chiral molecule, it will have optical activity. Okay, and when you say having optical activity, what that means is that the molecule itself can rotate what's called plane polarized light. Okay, and I'll explain what plane polarized light is in a minute. Okay, so a molecule that's chiral can rotate light, or that plane, to the right. A molecule that's chiral can rotate light to the left. Okay. All right, this is really important, so put a star in your notes next to this. R and S for stereochemistry is not related in any way to the molecule's ability to rotate light, or the molecule's ability to rotate light to the left or the right. Okay, so if you have a molecule that's stereochemically labeled R, which means if you take your steering wheel, the priority will turn the steering wheel to the right. That doesn't mean that that molecule will rotate a plane of light to the right. Okay, an R stereochemistry might rotate light to the right, but R stereochemistry might rotate light to the left. It's a property of the molecule that you would actually have to do the experiment in order to determine that rotation. There's nothing that you can do by just looking at a molecule as a drawing on paper to determine the rotation of light. So the two molecules that we're going to compare are going to be a set of enantiomers. So the first one okay, this is a dash here, or sorry, a wedge. So these are molecules of a compound called carvone. And carvone has a smell, but the smell depends on which enantiomer you pick or you have. One of them smells like spearmint. I can't remember what the other one smells like. This is called R-carvone. This is S-carvone. And that would be by going in and doing the stereochemical analysis at those two carbons. All right, I'm going to erase the top of this. Okay, so R and S carvone represent a pair of enantiomers. Okay, this is my bad pen. Let me change it out. Okay. When you have a pair of enantiomers, they're going to have, oops, no, maybe that was the good one. They're going to have the same melting point, same boiling point, same intermolecular forces, same behavior on a separation column. The other type of thing for a separation column is called thin layer chromatography, which I'm sure you'll have a lab on at some point. Thin layer chromatography has to do with if you have a little thin sheet of silica, you mark a line on it, and then you put your samples here and here on the line. So let's say this is R carvone and this is S carvone. And you take this thin layer chromatography and you put it into a beaker, and the beaker has solvent in it. Okay, and the solvent is going to climb the TLC plate, and it's going to move these molecules. So that at the end, for this particular set of enantiomers, when you look at your plate, there's your line of origination. R carvone would be here, S carvone would be here. So they're going to travel the same with respect to the attraction to the plate versus the attraction to the solvent. So that's why separation of enantiomers is so difficult, and why oftentimes pharmaceutical companies don't separate enantiomers, because you need a special type of separation to do that. Okay, but in terms of their rotation of light, R carvone rotates light to the left, which is given a minus, by 61 degrees. Okay, so here's an example of an R stereochemistry molecule that rotates to the left. Okay, that's called being levorotatory, which means rotate to the left. Now, S carvone will rotate the light to the right. Same magnitude, opposite direction, so plus 61 degrees. Those are called dextrorotatory. Okay. If you took R carvone and you put it, and I'll show you, I'll draw a diagram of what the optical activity instrumentation looks like, but if you put R carvone in, and only R carvone, like you have a pure sample of it, and you find that it rotates to minus 61 degrees, you automatically know that its enantiomer will rotate equal in magnitude, opposite in direction. Okay. All right, are there any questions about that before we draw the diagram? Okay. So we're going to draw it from left to right. And it's important to remember that this property is associated with all chiral molecules. Okay. All right, so where you start is you have a light bulb, some light source. Okay. Now, as the light comes out of this light bulb, it's going to be in all planes, which means you'll have a plane of light like this, a plane of light like this, all throughout your, it's like the light comes out in all planes. Okay. Then you have this piece of instrumentation that has slits in it. Okay, that's called a polarizer. Okay. Only the light, so remember H nu is the symbol for light. Only the light that perfectly matches the slits passes through. All other light is blocked. Okay, so in this drawing here, I'm going to replace this one that was vertical with this red line. Okay, because this red line is going to match up perfectly with these slits in the polarizer. Okay, so that what comes out of the polarizer is a single plane of light. So then what happens is this plane of light enters the sample chamber, and the sample chamber is like a tube. The dots are the molecules. And it's in that sample chamber that the chiral molecule rotates the light. It doesn't bend it. It's not like the plane is going to go from this to this. I'll have a piece of paper. Okay, so I'm not going to bend it. It's just the plane, the light is passing through the chamber with the molecules, and it goes like this. It either bends or not bends. It either tips to the right or it would tip to the left. So it's not doing this. It's just a vertical plane is going to rotate in some direction. Right. The light exits the chamber then at an angle. Okay, so this is light out. This is one plane of light in. This is the rotated plane of light out. Then you have something, another thing that looks like this, which has slits. And it's called the analyzer. Okay, and the analyzer rotates. You can either move it in this direction or move it in this direction. Okay. The light started out like this, ended up like this. that angle is called alpha, and that's the rotation of the light. Okay. So this would be measured. Oops, you can't see that word. I'm going to measure alpha. Okay. Now, alpha, what you measure in your experiment, is dependent on several things. It's dependent on how long this chamber is, as well as how many molecules are in there. Okay. So what we report is a normalized degree of rotation, and it's called alpha D. That's called specific rotation. Specific rotation is what you would look up like in a manual. Now this D is referring to a reference point which is related to a property of sodium. Sodium, when you burn it, like if you don't do this at home, but if you, please don't do this at home, but if you take table salt and you soak it in rubbing alcohol and light it on fire, it's going to burn yellow because of the sodium. So it's like it's a line of reference, a point of reference. I only know this because I actually did it at home and my mom freaked out. Okay, so your specific rotation is going to be equal to your measured rotation. So this is instrument dependent, divided by the path length, which is the length of the chamber, times the molarity concentration of your sample. And so that's how you would measure it. And the eyeball of the person obviously is right here. Questions about how that instrument works?
What was the value in the brackets again?
This is concentration. Square brackets means molarity.
Okay, thank you.
Yeah, which is moles over liter. Any other questions about this diagram? Okay. All right, so let's say now that we are going to do this experiment. And we're going to do it in a couple of ways. So our experiment, and we're going to write percent R carbone, percent S carbone, and then the optical rotation. All right. So in experiment 1, we're going to put in 100% R carbone and 0% S carbone. So we have a pure sample of R. We would do the measurement and we would normalize to find out that our rotation is minus 61 degrees to the left. Okay. Now this one we did. Okay. In the second one, we wouldn't actually have to do the experiment. If we just switch to the other enantiomer, we have to have the same magnitude in the opposite direction. Okay. Now in experiment 3, we're going to put in 50% of the levorotatory molecule, 50% of the dextrorotatory molecule. Okay. Does anybody have a guess at what the optical rotation will be if it's 50-50? We got to vote. Somebody's coming in on a chat. 0. Karen says 0. Okay, can you go into your participants and tell me if you agree? Do you think it'll be 0 or yes or no? Perfect. All right, so we have 13 votes so far. They're all yeses. That is correct. This will be 0. So for every one molecule that rotates to the left, you have a matching one that rotates to the right. This type of mixture, when you have a 50-50 mixture of enantiomers, that's called being racemic. So that's a racemic mixture. It contains chiral compounds, both of which independently will rotate light, but when they're combined, you see no optical activity. Right. Now here's a fourth experiment to think about. What happens if you had 63% R, 37% S? Okay, and we don't do math so much in this class, so we wouldn't have to calculate the number. So I'm not asking you for a number. I'm asking you for a direction. Will it rotate to the left and be levorotatory, or to the right, dextrorotatory? What do you think? Okay. For this type of question, all you have to do is look at which of the enantiomers is in excess. So since the R enantiomer is in excess, you'll rotate to the left. So that's all you would have to do. You wouldn't have to predict a number, but you would have to be able to say, if R rotates to the left and this mixture is mostly R, then you would have a left rotation of plane polarized light. Okay. Questions about this before we move on to a new type of stereoisomer? Okay. All right, so this is 5.5. Okay, and this section is on enantiomers and a new type of stereoisomer, which is called a diastereomer. Everybody wants to say disaster, but it's diastereomer. Okay, so we're going to draw this flow chart, and the first thing we're going to do up here is we're going to say that our header is this whole topic of isomers. Okay. So the first branch is between constitutional isomers versus stereoisomers. Constitutional isomers have different connectivity between the atoms. So we've seen constitutional isomers. We saw those the very first day of class when we looked at 1-propanol, isopropanol, and methyl ethyl ether. They have the same formula. They're all C3H8O. but they have a different connectivity between their atoms. Okay. Now, stereoisomers have the same connectivity, but they have different 3D arrangements. Now, because they have different 3D arrangements, all stereoisomers are non-superimposable. That's true of both enantiomers and diastereomers. So they're always non-superimposable. Okay. The difference in stereoisomers, I'm going to bring one over here, is that if you have enantiomers, they're non-superimposable, but they're mirror images. Okay. If they're non-superimposable, but they are not mirror images, they're called diastereomers. Okay. They're not mirror images. Okay, so let me see. Okay, so the way to think about this, if we go back to enantiomers and you put your hands up so that they face one another. Okay, we've already discussed that if you have a mirror plane, or you put your left hand up to a mirror, the reflection is going to be your right hand. So these are non-superimposable because I can't line them up perfectly, but they're mirror images. Okay. Now, this is like saying your left hand versus your right hand. Okay. Diastereomers is like comparing my right hand to your right hand. Okay, so if you look at my right hand, oops, okay, they're non-superimposable because we don't have the same shape. Fingers, like look at my crooked witch finger, okay? You don't probably have a crooked witch finger on your right hand. Andrew might have a crooked finger, but most of you probably, hopefully don't. Okay, you also don't have a partner that makes you cut your finger on a damn cheese grater, okay? So my right hand, oops, let me get it in the screen, looks kind of like your right hand, but there are differences. Our right hands are non-superimposable and they're not mirror images. Okay, and so those are called diastereomers. Okay, now the way that you, oh, let me write that over here. So my right hand, your right hand. I will tell you though, y'all, my husband felt terrible about the cheese grater, but I'm never gonna let him forget it. My right hand, your right hand. Okay. All right, so enantiomers, they have to be perfectly opposite at all chiral centers. Okay. Diastereomers will be opposite, and I mean configuration, RS, opposite at some, not all, chiral centers. And we'll draw some, I have some examples, but I just want you to make sure that you have the flow chart worked out. Okay. All right, does anybody have any questions or need any more time drawing out this flow chart? So I'm going to erase it and then rewrite a little bit of this bottom stuff. Okay. Okay. All right, so we're going to have a couple options. Okay. So, and then I'll do other ones over here. So a pair of enantiomers would be, one is R, the other is S. Okay. Let's say in the second example, we say our first enantiomer is S at one chiral center and S at another chiral center. Okay, in order to be enantiomers, they have to be opposite at all chiral centers. So the enantiomer would be R, R. Okay. The third example we'll say is R, R, S. So 3 chiral centers. To be its enantiomer, it has to be S, S, R. So you only have one perfect opposite. Okay. Now, if you take your RRS molecule, okay, the list of diastereomers is going to be much larger, okay, because you can be opposite just here, like S, R, S. You could be opposite just here, R, S, S, opposite just here, R, R, R. You could be opposite at 2, S, R, R, S, S, S. The list is long. Okay, so a chiral molecule has one enantiomer. Chiral molecules have many diastereomers. Are there any questions about that before I give you a couple? Oh, wait, I'm going to show you some examples and then I'll give you some questions to practice on. Okay. All right, so let's look at a molecule with 2 stereocenters. So I'm going to draw it flat, cyclohexane disubstituted. Okay. We have a hydroxide and we have a methyl. Okay. All right, so the first thing to do would this be to draw one stereoisomer. So you would just pick, okay? Both dashes, both wedges, one dash, one wedge, whatever you pick. I'm going to start with both of mine on a dash. Okay. The perfect opposite is to have both on, I said that wrong. So these are both wedges, these are both dashes. So this is a perfect opposite. So these are enantiomers. Okay. The third would be a dash and a wedge. Its perfect opposite would be dash hydroxide, wedge methyl. Okay, so now these are perfect opposites. So these are enantiomers. Okay. This one and this one, or this one and this one, or this one, this one. The relationship between one from here and one from here, those are diastereomers. Now you can go in, we're not going to put the time in to do this in class, but if you want to do it on your own, it's a good exercise. This is R and this is S. So this would be S and R. R, R, S, R. Wait, no, SS. Okay, so you can go in and, so to determine enantiomers and diastereomers, you can assign R and S. Or you can look at the bonds. Looking at the dash and wedge bonds is the fastest way to determine the relationship enantiomer versus diastereomer. R and S will be more time consuming, but will also get you the same point. Now, before we move on, you can say that this is cis and this is cis, trans, trans. Okay, so cis and trans is called relative stereochemistry. So it's giving you a relative relationship, same side, different side of substituents off the ring. R and S is called absolute stereochemistry. Okay, so cis trans is relative stereochemistry. They're both correct. It's just two different ways to say the same thing. R and S, it's called absolute. All right. Now, one other thing before I give you some practice. This compound has 2 stereocenters. So if you want to know how many possible isomers you can get, you take 2 to n, where n is the number of stereocenters. And that's the maximum number of stereoisomers possible. And n is the number of chiral carbons. Any questions about that before I give you two? I'm going to give you 2 pairs of atom or molecules, and I want you to pick whether they're a pair of enantiomers or a pair of diastereomers. Okay. Right. So you guys work on these for a little bit and determine if the top two are enantiomers or diastereomers, and the same with the bottom. Okay, so don't make a relationship to the top and bottom, just across left to right. Whoa, so sorry. Okay. Does anybody want or need more time on this example? Okay, I'm going to take that as a no. Okay, so the way I would do this is I would look at what is the change in the bonding from here to here. Okay. If the methyl on the wedge becomes a methyl on a dash, then the unwritten hydrogen also has to change. So those are opposite configuration. This goes from methyl on a dash to methyl on a wedge. That's also opposite. So if they're opposite at all the chiral centers, they're enantiomers. Okay. Down here, you go from hydroxide on a dash, wedge, to hydroxide on a wedge. Methyl on a in plane, methyl in plane. This group in plane, it's still in plane. Hydrogen on a dash, hydrogen on the dash. These are the same. Okay, but down here, you go from having chlorine on a wedge to methyl on a wedge, methyl in plane to methyl on a wedge. So these things are different. When you have some are the same, but the others are opposites, these are diastereomers. Okay, if you would get same, it means it's the same compound. Okay. Questions about that? How to recognize enantiomers or diastereomers? Okay. Right. So we're going to expand on this and include now what's called molecules with an interior mirror plane. Okay. Meso compounds. So we said that 2 to the n will give you the maximum number of stereocenter or of isomers, stereoisomers. Okay, but you have to be careful in compounds with interior mirror planes because you could end up repeating a stereoisomer. Okay, so for example, if we take this flat compound with 2 stereocenters, both with hydroxides. Okay, so we draw one wedge dash. We flip the stereochemistry by changing to dash wedge. So these 2 in the red box these are enantiomers. Okay. But now, when we draw the second set, these are the same compound. Okay. And what I want you to think about is if you take this molecule that has the 2 hydroxides on the dash, and you put a spatula under it and you flip it over, you're going to end up like this, a ring with 2 hydroxides on wedges. So these 2 are just flipped. These are pancake flipped to get to one another. Okay. That happens when the stereoisomer has an interior mirror plane. When the top of the molecule or one side of the molecule is mirrored into the other side of the molecule. So this hydroxide reflects into this hydroxide. This CH2 reflects into this CH2. This CH2 reflects into this CH2. Okay. When you have these, this is called a meso compound. Okay. Meso compounds will have no optical activity, because any rotation of the light that occurs due to this chiral carbon is equal but opposite to the optical activity at this chiral compound. So meso compounds themselves end up with no optical activity. These 2 would have optical activity, equal but opposite from one another. Okay. Meso compounds must have an even number of chiral centers. And they have to be reflected into one another. Any questions about meso compounds?
I do have a question.
Sure.
So would that structure to the right of that meso compound not also be a meso compound?
It's not an isomer because it's the same as this one. So in this compound, you don't get 4 stereoisomers, you only get 3, because this one and this one are the same. So this one doesn't count.
Okay.
Andrew, I can't hear you talking. Can you oh, there you go.
Okay. So the 2 molecules you have on top, if you flipped one of them vertically, would that not be the same as what you're doing?
No, because if you take this molecule and you flip it over so that this carbon is now on the top, this hydroxide is going to be on a dash, and it is not on a dash here. Let me see if I can find my ring. I don't have 2 built.
That's fine. I'll
like
play around.
this. Look at it like this. Okay, so can you see my molecule? Here, let me put myself back up. There we go. Okay, so I've got a ring. The yellow is closest to me up. The green is closest to you down. So that looks like this. Okay, if I flip it like a pancake, now green is closest to me and up. It had been closest to you and down. So I won't be able to get it to superimpose. But if you don't believe me, and it's fine if you don't, you should build the models and try to get them to overlap, and you'll find out that they can't. But if you build
I believe you.
Okay, thanks. Down here, if you build them, they will overlap. But if you build these 2, they won't. If they overlap and they're superimposable, let me see, so to be a stereoisomer, you have to be non-superimposable. So if they superimpose, they're the same compound.
Okay.
So because we're always talking about things in a pair. So if you're talking about you have a pair of molecules and they're non-superimposable, but they're mirror images, then they're enantiomers. If they're non-superimposable and they're not mirror images, they're diastereomers. If they're superimposable, they're the same compound. And it may not be easy to see the way I've drawn these, that these are mirror images. So let me take off this mirror or the meso compound right quick and redraw. Okay, now if I rotate this, not flip, but rotate it around, just like turn it like on a record, it'll line up like this. And then here's your plane of reflection. So they're mirror images, but they're not superimposable, so they're enantiomers. Non-superimposable mirror images are enantiomers. Non-superimposable non-mirror images are diastereomers. Okay, and if you wanted to see a diastereomer set, okay, so same, opposite. So they're diastereomers, but they're also not reflections because this is going down and this one is coming up. Does that make sense, Andrew?
Yes, it does. Thank you.
Yep. Any other questions? Okay, so the last thing we're going to do is talk about what's called a Fisher projection. These are not the same as Newman projections, but Fisher projections. So this is section 5.7. hope I spelled, yeah, I did. Fisher projections, okay? And Fisher projections are, Annie, are there always going to be 2 chiral centers? No, there could be 4, there could be 10. It's going to just depend on the size of the molecule. But if you have a chiral molecule that has multiple chiral centers, so I mean, it's going to be hard. I'm going to have to draw it purposefully so that it you can tell that it's got a plane. So let's say so this one has 1, 2, 3, 4, 5, 6. So 2 to the 6. I need a calculator to do that. Oh gosh, I don't have one. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. How many is that? 1, 2, 3, 4, 5, 64. 64 stereoisomers maximum. That's a lot, okay? But if you look at this, of these 62 or 64, you're going to have one that's a perfect set of enantiomers. This particular drawing has a mirror plane right through the center. The hydroxide reflects to the hydroxide, the fluorine to the fluorine, iodine to the iodine. So of these, this one is meso. So you can't have 34, you'd only get 33. Well, you'd get no more than 63. But meso has to have an even number of chiral centers, because if this isn't a chiral center here, it's reflecting into a chiral center here, and then it's not meso anymore. But you could have tons of chiral centers in molecules. Obviously, I'm not going to ever ask you to draw me 64 different stereoisomers, so don't have to worry about like drawing that many things. But you should be able to look at 2 things and make a relationship. Okay, great. Okay, so Fisher projections, these are really common in biochemistry to show sugars, starches, and complex carbohydrates. So I'm just going to show you what one looks like, and then we'll do an assignment on it. It's going to have, let's see, just 2 chiral centers. Okay, so Fisher projections, your carbon chain is shown as a line, a vertical line. Okay. Then what you end up with is you have like crosshairs on your Fisher projection. And these are your chiral carbons, okay, because they're still shown as sp3 because they have 1, 2, 3, 4 bonds off of them. So they're sp3 carbons. And then let's just say here we have a OH. So that's a carboxylic acid group at the top, carboxylic acid group at the bottom. Okay. So these left to right lines on the Fisher projections are typically hydrogens and hydroxides, but they can be other things too. So let's just draw a hydrogen and a hydroxide, hydroxide, and a hydrogen. Okay. So with Fisher projections, the horizontal lines are both wedges. Okay, so you're kind of looking at your molecule like if you take this is kind of gross because I don't like bugs very much, but if you have like a centipede, it has the body on the top and then all the little legs on the bottom. And if you take that centipede and you flip it over, then you have the body on the bottom and the legs up going like this. Okay, so that's what these are like. They're like an upside down centipede. Okay. So the horizontal lines are both wedges. So what you're going to do is you're going to draw a bow tie on the horizontal lines. Okay, so you come in like this and like that. Okay, and you do the same thing down here. Okay, and so you draw your bow tie on horizontal lines of chiral carbons. Okay. Then what you're going to do is you're going to assign priority for R and S. And then here's the thing that you got to remember, because the way that the Fisher projection is drawn, the hydrogen is always in the wrong spot. It's never going to be shown going down or away from you on the steering column. It's always going to be shown up. So after you get your assignment, the answer for chirality is opposite. Okay, so we'll do this together, and let's say we do the assignment on something and in a Fisher projection, and our assignment is a right-hand turn, so we say it's R. The actual molecule is reversed, so it's S. So in this case, the Fisher projections, you always do the opposite of your assignment. So we're going to start up at the top, this chiral carbon here. Okay, the nice thing is the rules are still pretty much the same. The lowest priority group gets 4. And now we have a carbon, and an oxygen. So the oxygen will be 1. Okay, carbon here to carbon here. So we have to look at the groups off these carbons. This carbon at the top is bonded to oxygen, oxygen, because it's on a double bond. So oxygen, oxygen, oxygen. This carbon down here is bonded to an oxygen, a hydrogen, and a carbon. So 3 oxygens beats 1 oxygen. This is 2, and this group down here is 3. So when we do the configuration here, and we can connect 1 to 2 to 3, okay, this looks S, but it's going to be R. Okay, so you always just invert whatever you assign. Down here, hydrogen is 4, hydroxide is 1. This carbon and this carbon, these two are tied, so you look at the groups bonded to those carbon atoms. This carbon is bonded to oxygen, oxygen, oxygen. This carbon is bonded to oxygen, oxygen, hydrogen, carbon. So the set of 3 oxygens beats this. So this is 2, 3 is at the top. Draw your connecting line, 1 to 2 to 3. This looks like S, but you flip it and it's R. So this Fisher projection is RR. Are there questions about the Fisher projections? These are another thing that they just take some practice. I'm happy to give you a practice problem if you want one. Otherwise, we can be done with chapter 5. You can work on it a little bit. Maybe we can touch on it tomorrow and we can move on into acids and bases. What do y'all think? Okay, since there are no votes, I'm going to move on to chapter 3, but I have to go find my notes real quick. All right. Okay, so chapter 3 is acids and bases. Okay. Okay, so we're going to start with the Bronsted-Lowry definition, or the Bronsted-Lowry model of acids and bases. Now, this should be a review from general chemistry. And we're going to draw something pretty silly, but it makes sense. So we have 2 people, very happy. Okay. The one on the left has a ball. Okay. The ball represents the proton. Okay. So the guy who has the ball is the acid. He's going to be the proton donor. Okay. He's going to throw the ball to the other person. That's the base, the proton acceptor. Okay. What that's going, I'm going to make this person, and I don't wear skirts much either, but it's the only way, it's going to be the easiest way to distinguish these. So we have a guy and a girl playing catch. Okay. If you don't like skirts, or you wear whatever you want. I don't care. I just have to have something. Okay. So then over here, the man no longer has the ball. The lady does have the ball. Okay, so the Bronsted-Lowry model of acid bases is a proton transfer. Okay, but the only way to successfully have a game of catch is she's got to throw it back. So in the reverse reaction, that's going to go in this direction. She throws the ball back to him. Okay. If on this side, he is the acid and the proton donor, on this side, he's the conjugate base proton acceptor. For the reverse reaction to take place, he has to get the ball back. And anytime you take a proton back, you're a base. The girl here is donating, so she's the conjugate acid proton donor. Okay, so when you have a Bronsted-Lowry model of acids and bases, you get a partnership. You have an acid that forms a conjugate base and a base that forms a conjugate acid. Okay, now the word conjugate just means to link. Like if you think about conjoined twins, that's when 2 people, like twins, are born, but there's in some way a physical connection between them. So the word conjugate only means it's linked to another species. Okay? If you have a proton donor, you have to have a proton acceptor. Okay? So we're going to, for a long while, draw this with an equilibrium arrow, even though we're going to see that in some cases, we have only a one-directional arrow. Now, if instead we don't look at people playing catch, we look at a chemical reaction. Okay. We're going to say that we have HCl, and we're not going to worry about phases right now, reacting with water. And like I said, we're going to keep the equilibrium arrow for a while. This species functions as an acid, so it's going to donate an H+. So a proton is a hydrogen cation. It's going to donate the H+ to the water, and what will be left over is a chloride anion. So now this is a base. It's the conjugate base of the HCl, so this is a conjugate pair. And they differ only by one proton. Okay. The water is the base, so it's going to take the proton. This is a donor. This is an acceptor. And we'll make H3O+. That's called hydronium. This is the acid. And these represent a conjugate pair. Okay. So if this reaction goes backwards, then the acid has a proton to donate back to the base. This side of the reaction is neutral. HCl is neutral, water is neutral. If you add the charges on these ions, the chloride -1 plus the hydronium +1, you are also neutral. Good? Okay. So what we're going to do now is we're going to start to use curved arrows to show reaction progress. Now it's going to be easier if you consider the electrons to be particles at this point, not waves, so that they can kind of like do a job. So your curved arrow is going to have to be a double barbed arrow, because we're going to use electron pairs to move the proton. Okay, so in the Bronsted-Lowry definition, and it's true all over in every general chemistry class, you're told that acids are proton donors, bases are proton acceptors, and it makes it sound as though the reaction proceeds when the acid decides to let go of the proton, but it's actually the reverse. The reaction proceeds when the base pulls the proton off of the acid. When you use your curved arrows, the tail of the arrow has to start on electrons, always. They can be lone pairs of electrons, they can be pi bonded electrons, they cannot be sigma bonded electrons quite yet. Pi bonds or lone pairs, and they're going to go to an atom. So we're going from a negative region to a region that may be positive. And if you look at something like HCl, it has a dipole moment like this, where the hydrogen is partially positive, so the electrons can go and grab a partially positive hydrogen. Chloride is partially negative. Okay, so now for a while, you're going to get the reactants and the products, and you would have to interpret or draw the arrows that would create the products shown. Eventually, you'll do product prediction. Okay, So where we're going to start, I'm going to do one and then I'm going to have you do one on your own, is we're going to take hydroxide. Okay. Let me move that down just a little bit. And we're going to react it with a carboxylic acid. Okay. And when we do that, what we're going to make is water and acetate. Okay. So this sort of thing would be given, and you'd have to determine how to use curved arrows to take these things and make this thing. Okay. So the species that are related, hydroxide is related in a conjugate acid and base pair with water. The acetic acid is linked in a conjugate acid base pair to acetate. Okay. So in order for the hydroxide to end up as water, it has to take a hydrogen from acetic acid that's polar. So there's some CH3s over here. Okay, but these are non-polar hydrogens because they're bonded to carbon atoms. This is the polar hydrogen. Okay, there's the dipole moment. So in order for hydroxide to make water, it has to take that hydrogen cation. So one of the lone pairs, it doesn't matter which one you use, has to come over and grab that hydrogen. Okay. Hydrogen is not going to take these electrons with it. So what I'm showing is the formation of a bond from hydroxide to that hydrogen. I'm going to form a new sigma bond. Okay. If that's all I draw, this hydrogen is going to be bonded to the hydroxide as well as to this carboxylic acid, and hydrogen can only ever make one bond. So what happens is these sigma electrons go onto the oxygen so that this oxygen becomes, or this acetic acid becomes acetate. So it goes from neutral here, 2 bonds, 2 lone pairs, to negative charge here, 1 bond, 3 lone pairs. And I make water and acetate. Okay. In both cases, the tail of my arrow is on electrons, moving up, going to atoms. The barb is pointing to an atom. Okay. So I'm going to leave that up here. And what I want you to do is I want you to take this compound and this one, and I want you to make this and that. Oops, that's a negative. And what I want you to do is draw arrows on this side that will form these products. Okay, so this thing, just so that you know some of the names of these things, this is called tertiary, I'm just gonna abbreviate with a T, tertiary butoxide. You know that's water. This is called tertiary butanol and hydroxide. Okay. All right, so in order, these two things are related by the transfer of a proton. So the tertiary butoxide has to gain a proton. So it's the base. It needs a proton from water. So water is the acid, the proton donor. Tertiary butoxide is the base, the proton acceptor. Okay, but remember, the base takes the proton off of the acid. So you can use any of the lone pairs you want. Okay. Go and get the hydrogen. That makes a new sigma bond, but then you have to end up with hydroxide. So in order to break the hydroxide off, these electrons go up onto the oxygen atom and you make hydroxide. Okay. Are there any questions about if you see reactants and you see products, can you draw a curved arrow to show proton transfer? Okay, I'm going to erase the bottom and we're going to keep this reaction up here on the top. Okay, so this set of double-ended arrows here, okay, that is the equilibrium set of arrows. Okay, and the position of equilibrium is given by K. So K is the equilibrium constant where you have your product's concentration over reactants. Okay. Right. So what we're going to work on is we're going to look at what are called pKa values. Okay. So the P is putting the equilibrium constant onto a log, an inverse log base 10 scale. So pK is equal to the inverse log of the equilibrium constant. So the bigger K is, the smaller pK is. Small pK is equal to a large K. The little a here just stands for acid. So we're looking at acid equilibrium constants on an inverse log scale. I'm not going to ask you to do the calculation, but I did at the beginning of the semester ask you to start memorizing some pKa values for some common organic molecules. Okay. And I'll get to that, I think, today, but we're going to do a little bit more with Ka. And in order to refresh Ka, we're going to write the generic equation for acid dissociation. So HA just means some acid reacts with water to form the conjugate base and the hydronium cation. If you take the inverse log of this concentration, you get the pH. Anytime you make the hydronium cation, your reaction is described by an equilibrium constant for an acid. Acid equilibriums always make hydronium. So Ka is going to be equal to the concentration of the anion at equilibrium times the concentration of the protons or the hydronium cations divided by the acid concentration at equilibrium. Okay, now if you look at this, the water concentration is never in Ka. In an equilibrium expression, you never include the concentration of solids or pure solvents. Okay. If your value of K is large, greater than 1, that means the reaction is product favored. Or you could say the reaction proceeds to the right. It'll go more to the right-hand side. You'll have a high concentration of products. If K is less than 1, it means your reaction is reactant favored. This is my handyman. He's outside drilling in my house. Hey, Damon. I'm almost done teaching, but I don't need any water. Yeah, I'll be out in about 5 minutes. Okay, thanks, Damon. Reactant favored. Sorry about that. Okay, and like I said, we're going to simplify our K values to PK values, or Ka values to pKa. Okay. The lower the pKa, the stronger the acid. Okay. Now, if you remember from general chemistry that there are 7 strong acids. And the 7 strong acids are all K greater than 1. And in general chemistry, we didn't give them to you because they didn't matter for equilibrium calculations or pH calculations, but they're on the order of like tens of thousands. So the strong acids are HCl, HBr, HI, HClO4, that's called perchloric, chloric acid, nitric acid, and sulfuric acid. So all of those 7 are your strong acids. Now they're not equally strong, but they are considered the 7 strong acids. Everything else is a weak acid. So I'm gonna pull up a slide from the notes unless there are any questions about what I have on here. And then we'll just do one more thing and then we'll be done for today.
For K less than 1, the reaction heads to the left on that instance, right?
Mm-hmm. Yeah, it's left-hand side favored, which just means that the concentration of the reactants will be greater than the concentration of the products. Does that make sense?
Yep.
Okay. All right. Let me quickly pull up that chart. I put up all the annotated slides for the rest of the semester as well as all the lecture slides because I can't remember to do it at the exact right time. So I'm done with that. Doing it a little bit. Okay, here we go. Oh gosh, it's the wrong dang chapter. Sorry. Okay. Right. So we're going to start at the top here. And this is from your text. So if you look up here, you have sulfuric acid, you protonated ketone, you don't need to worry about quite yet, but HCl is up there. These are all, this is your strong acid region. So you can tell sulfuric acid is a stronger acid than HCl. Okay. The stronger the acid is, the weaker its corresponding conjugate base. So you can see that sulfuric acid, and this is called bisulfate, and bisulfate differ by 1 proton. So if this is a very strong proton donor, this is going to be a very weak proton acceptor. Weak to the point where it's so unreactive, it won't take protons from other places. Okay. Same thing is true with HCl. HCl is a very strong acid. Chloride is a very weak base. Okay. So the ones that I asked you to look at or memorize are knowing that the strong acids, the 7 strong acids, have negative pKa's. Here is your carboxylic acid. So carboxylic acids are around pKa 5. This one right here, we'll come to why it's lower than the other alcohols in a little bit. This one is called phenol. So it has a benzene or an arene ring with a hydroxide. It has a pKa of 10. Water and other alcohols, you can put about 15 or 16. Ketones are about 20. This one we'll come back to at the very end. The terminal alkyne, 25. Alkenes, 40s, mid 40s. Alkanes, 50 or higher. So on the left-hand side, there's strong acids at the top, weak acids at the bottom. The weaker the acid, the stronger its conjugate base. So it's an inverse relationship. If you have a strong acid, it's related to a weak conjugate base. If you have a weak acid, it's related to a strong conjugate base. You can have cases where you could say, well, this is a weak acid and this would be a weak conjugate base, but we won't worry too much about stuff like that. So you don't have to memorize this list, you just need some targeted points. Okay. Are there any questions before we end for today? Okay, so I will see you guys tomorrow. Check your grades on Canvas. They should all be curved. And those will be the grades. I haven't done anything with the ALEKS scores yet. And I know some of you like moved on and then it adjusted a few things. So I have to work on that, but it's going to take a chunk of time. So I just haven't started, but I will get to that shortly. All right, well, if there are no other questions, then I will see you guys tomorrow. Have a good rest of your day. So it looks pretty out.
Dr. Walters, I did have a question about the
Yeah.
that one question that I sent you to the email, the one that had that sorry, I know I sent you a lot, but the one that had the arrow that was kind of pointing.
Oh yeah, I remember. Can we talk about that one separately?
Yes.
Okay. Anything else?
That was it for me.
Okay. All right, so.
Thank you for class.
Wait. Yes?
Thank you for class.
Oh, you're welcome, Hannah. Have a good one.
You too.
Thanks. See you tomorrow. All right, let me stop the recording.